So now that we have seen exactly how the measurement of fracture toughness is done and the peculiarities in the process, let's see also some other interesting practical aspects related to fracture toughness. What you see here on the screen is a data sheet for an industrial aerospace alloy 7475, which is one of the alloys that they have been developed over the years for aerospace applications, which are very critical with respect to fracture toughness. And there are a couple of interesting things that I want you to notice here. The first one is, first of all, have a look at the chemical composition limits. They do vary a lot. And that is interesting because essentially everything within this range is acceptable, but there are implications with respect to properties. And the interesting thing that you see down here is, in addition to typical fracture toughness values, there is something that's called guaranteed minimum fracture toughness value, which is obviously something that can be guaranteed only with quality control, and of course you have to pay for it in the price of the material. So essentially it tells you that every part that comes out of production for this material has a guarantee value like this one here, but typical values may be higher. However, there may be some variability there. So one of the things that I want you to have a look at, and let me erase the ink here, is the fact that there are two values that they are reported here. There's an interesting LT designation here and a TL designation there. Which is relatively unusual in the sense that it indicates that there are two different values, and if you look at this detail of the diagram here of this graph, you will see that essentially as you produce, and this is a plate, right? And you can see this is the rolling direction, this is the transverse direction, and this is the through thickness direction. As you will see, you will understand that when you are producing a microstructure through rolling, there are significant variations in the properties from one direction to the other. And so TL actually corresponds to this sample here. Okay. And LT corresponds to this sample here. Okay, and this guy here has actually a better fracture toughness than that one. And it is interesting to see and think actually what is the origin of this anisotropy in fracture toughness, because rolling actually implies two things. Let me actually try to draw a schematic. So the grains of the material that may be roughly equiaxed before rolling actually will become elongated after rolling. And so that is what we call the morphological texture. And the next thing, it has to do with the orientation. The process, the substantial plastic deformation of this process is going to actually create preferential orientations for the grains in the systems, because plastic deformation implies that the crystal lattice essentially rotates, and this rotation produces systematic orientations. They are no longer actually randomly oriented. And so these two differences are responsible for the fracture toughness of the material, and it's really interesting to see that this kind of microstructure, and of course I'm actually being rather careless here, but you get the idea. And so once you have this microstructure in your mind, then actually it's not really unusual to see this difference. So if you have a specimen that has a crack oriented this way versus a specimen that has a crack oriented that way, it's not unexpected to have this actually have a larger fracture toughness than that. And there are some empirical arguments that can be used for this. So for example, people say that the defects are actually scaling with the grain size, and in this case the grain size is not isotropic, so defects in this direction here are going to be proportional to this size, while defects in these directions are going to be proportional to that size. And obviously this kind of defects will reduce the performance of the microstructure in that direction. Although this kind of argument is not really accurate, because fracture toughness in theory is supposed to be independent of the defect. It has more to do with how energy it is absorbed as a crack propagates in this direction. And what you will see here is that the crack will propagate with very minor changes in path, while here a crack will have to probably follow a much more meandering direction. And maybe that's actually what is causing the difference. And so that reminds me actually to talk to you a little bit more, and we will in the next few slides, about the energy absorption other than plastic deformation. And we'll talk soon about this. Anyway, so I wanted for you to understand that fracture toughness, as with many other mechanical properties, is characterized by anisotropy, which in many cases is associated with the processing of the material. And as an example, you have seen this situation with this aluminum alloy that is used in the aerospace industry. Well, before we go there, I just wanted to repeat one more time a couple of the practical things that we can do with the values of fracture toughness that we have. So if you have a value of fracture toughness for a material, then you can do two things. First of all, you can say, okay, if I have certain crack size, okay, what is the stress that will actually make my material fail? And so in this case, you have something like this. I will actually ignore F, the shape factor, most of the times, but you need to keep in your mind that it's there. And so if you know this guy, then you can calculate this guy, and that's an easy analysis. So you can design your loads so that they do not exceed the critical values. Okay. The other situation is if you know your stress. So this has to do with design. And then the other situation is that if you know your stress, so if you have an existing design, then you can actually find out what is the critical crack size that will make the structure fail. And this is very important because you can use non-destructive examination techniques to verify that existing cracks are not present. And so how do we do this? I mean, the same calculation here, it's a little bit more complicated because actually the shape factor is often a function of the crack size. And so this is not a simple equation to solve, but you can solve it numerically. And you've seen how we solve these things numerically. It's not a problem. You should be able to do that. Okay? But the idea is that you have one unknown. You know this from your design, and then you can make a decision as to what is the critical crack size that your structure can actually afford to have without any major problem. So, what are the techniques that are used to detect existing cracks? There's a number of them, and there are some that they are really aiming towards surface cracks. Magnetic particles will align along the crack. Dye penetrant, a liquid that it will be absorbed by capillary into the crack, can actually give you a visual understanding of where these cracks are. And then we go into other techniques that they try to see things within the material using ultrasound. Obviously, if you have an internal crack and you send an ultrasound, you're going to have signals that they will be reflected from the back surface, and you're going to have signals that they will be reflected from the crack, and this difference actually gives you an interesting idea of where the cracks may be. In fact, you can do quantitative work with that. X-rays, if you can penetrate with X-rays your material, this is very common technique. And of course, electromagnetic testing, which in the presence of the cracks will actually modify eddy currents, and there are calibration techniques that will be able to give you some idea of the existing cracks. So if you can see the cracks, of course, that gives you an idea of what's the maximum crack. Of course, in some cases you won't, and what you do, you will not see them, and then what you do in these cases is that you take the detection limit of the method that you are using, and you make an assumption that your existing crack is actually the detection limit, and you do your calculations on the basis of that. Okay, and this is typically what is done in the case of aerospace structures. Let's see what we can do here. Okay, the last thing that I wanted to mention with respect to design is that, okay, we have done a lot of work and we have discussed things related to plane strain fracture toughness, and we discussed about the conditions for small scale yielding. In some cases, you will be able to satisfy these conditions, but in some cases, you will deal with geometries that are by default very small, and as a result, whatever condition you have, it's actually not going to be satisfied, and you have to deal with that. And I'm not going to discuss too much about this. I will just mention the existence of a technique that is based on what's called the J integral. The J integral, which is which was named J after the name of a famous professor with the name Jim Rice, who was responsible for the development of that technique that can be applied. It's a little bit more complicated than what we had discussed. Can be applied for specimens and geometries that for which the linear elastic fracture mechanics that we discussed is not applicable. So if you ever had to do with something like this, just go and read more about what's called the J integral technique that helps in those more complicated cases. I'm gonna skip this stuff just to go to a final discussion about the role of the microstructure. Up to this point, we discussed a lot about plastic deformation and its role in fracture toughness, and its role as a major energy absorption mechanism. But there are many other more energy absorption mechanisms that they are specific for a variety of microstructures. One of the most important mechanisms is what's called crack bridging. Crack bridging represents the situation where the two sides of the crack are actually connected, partially or fully, with some microstructural aspects like fibers or elongated grains. And the presence of these connections, if you wish, effectively reduce the stress and the intensity of stress at the crack tip. So remember that the stresses at the crack tip in general, they are proportional to the stress intensity factor, and that would be your F sigma square root of pi a. So that is for a fully open crack. If you have these fibers or microstructural elements that connect the two sides, the intensity that is felt by the crack tip from the same stress is actually reduced, because these connections actually provide for the support. And the way that this is done is either you have a fiber that essentially connects the two sides and it is still intact, that is, it's connected from both to both sides, so you have something like this, and this fiber is still attached at least further into the surface to the matrix, and this anchoring, if you wish, reduces the stress at the crack tip. Or if you have a process during which these fibers are cut, okay, you lose the support. But if the failure is such that allows for a frictional withdrawal of these fibers from one or the other side of the cracks, then you have another energy absorption mechanism that is due to the friction between the fibers and the matrix. And as I said, this can be done with fibers or can be done with phases of the material. For example, in this case, for silicon nitride, the beta phase of the material actually acts as a self-reinforcement because of the elongated shape that it attains in the microstructure. So you see the same kind of example. It's a very common technique trying to increase the microstructural contributions to fracture toughness for ceramics, and in a way can be promoted by the presence of weak interfaces. So the reason that weak interfaces play a role is that if the interface is very strong and a crack comes normal to the direction of the fiber, a strong interface essentially will get the fiber broken there. However, if you have a reasonably weak interface, and I put this word reasonably weak because it's important, reasonably weak interface, then it allows for this mechanism of fiber pullout to contribute to the energy absorption during crack propagation. So the weak interface design is a concept that was pushed for ceramic composites, I want to say in the end of 80s, early 90s. It is tricky. It is very tricky because if the interface is very weak, then there's a problem. If the interface is partially weak, then it helps. The only problem is that the presence of such an interface, it also provides path for things like oxygen and allows for interfacial reactions that essentially with time negate the contribution of such a optimized interface to the fracture toughness of the material. And of course, the transverse direction has a strength that is actually a fracture toughness that is quite reduced. And so the example of the performance of this kind of situations in the presence of and a reinforcing phase is shown here. So here we have silicon nitride, which is actually processed from powder and using a special technique which is called a spark plasma sintering technique with single wall carbon nanotubes. And what you see here are the baseline properties right here, and here are the properties with increased amount of carbon nanotubes. And what you see is that if the processing is very quick, so in that case there is an increase of the fracture toughness by the presence of the carbon nanotubes, but if there is processing at certain period of time, here about 3 minutes, that effect actually is reduced. There is an increase in the fracture toughness of the raw material because density and interfaces are actually being strengthened with temperature and the application of pressure in this case. But in the presence of carbon nanotubes, the interfaces are degrading, and in that case you see the smaller fracture toughness than the raw material. So these are actually the good and bad things of designing materials for improved fracture toughness on the basis of optimized but weak interfaces. And these are okay, there's no reason to talk about this. I mean, this is actually, well, anyway, we can talk about it. This is the whole story of the effect of carbon nanotubes on polymeric materials and the improvement of their properties. And what you see here is that a very small amount of carbon nanotube is adequate to increase the strength and maintain the ductility of the material. If you actually increase the amount of carbon nanotubes, maybe you can increase marginally the strength, but you're losing a lot because of ductility. And the reason for this is that with the increased amount of carbon nanotubes, it is very difficult actually to disperse them uniformly through the material. And as a result, the presence of a large amount of carbon nanotubes in an area, in an isolated area, which is difficult to be penetrated by the polymer, it may actually become a defect, and that is actually responsible for the reduction of the strength to failure. So in general, there are ways to improve toughness using fiber reinforcement. The result and the effectiveness of the result depend strongly on the specific of the system. In addition to the direct interactions, there are always indirect effects that they are associated with processing and its effect. And there may be issues related to sintering for ceramic matrices or dispersion issues for polymers. Okay, so there are lots of other techniques that they are providing, other micromechanisms that enhance energy absorption during crack growth. In fact, even anything that creates damage in the vicinity of the crack and distributes this damage around the crack tip is actually contributing. So microcracking and diffuse damage, which they sound like they would be bad, actually they are beneficial for fracture toughness reasons. In general, when you are designing materials, you have to realize that there is really no rules of mixtures in fracture toughness. You can, in fact, this is the variation of fracture toughness, adding, for example, zirconium oxide here in an aluminum matrix, and you see that there is a peak. So there is really, it's not like I take this and I take that and I get something that looks like this. In fact, you can have a synergistic effect in some cases where the optimum choice of the two components can give you a better result, but you can also have a worse result in some other cases. So the important thing to keep in mind No rules of mixture in fracture toughness. Okay, you really need to work much harder to understand what's going on in a specific system. To complete the discussions about the contribution of special microstructures to fracture toughness, the case of stabilized zirconia is an important one. It is a situation where a phase transformation during crack growth actually contributes dramatically to an enhanced fracture toughness. And it's not just restricted in the case of zirconia, but it's also common in the case of steels. In fact, the best steels that we have today are called the transformation-induced plasticity steels, or TRIP steels, which are offering the best combination of yield strength and fracture toughness. So let's have a look at the case of zirconia. What you see here in this phase diagram on the right, you see that for pure zirconia, at a range of relatively high temperatures, the crystalline structure is cubic. In the case of temperatures roughly between 1200, 1240 actually, up to 2300, it is tetragonal. And then all the way down below 1200, it is monoclinic. And so what we mean actually by stabilized zirconia is that if you add actually enough second phases like yttria, magnesia, and things like this, you can actually expand the range that cubic is the dominant microstructure. And in fact, actually, if you can have processing conditions that lead to remember that actually the phase diagram corresponds to equilibrium situations, and between equilibrium and reality there's kinetics, right? So you can have actually processing of fully stabilized zirconia in such a way that it remains cubic at room temperature, and this is the famous or infamous cubic zirconia, the fake diamonds, if you wish. Now, if you add a smaller amount of some of these phases, you have what's called a partially stabilized zirconia, in which you can actually process the material so that it is still primarily cubic zirconia, but with precipitates that they are below a certain critical size, that they have tetragonal structure. So you have C, cubic phase, and tetragonal precipitates. And those tetragonal precipitates, tetragonal phase precipitates, can actually undergo phase transformation to monoclinic under stress. And in fact, this transformation to monoclinic includes a change in volume. And it is really that change in volume that actually changes really the stress state at the crack tip. And usually the explanation is that the transformation takes energy, and that is really what increases the fracture toughness, which is sort of true, but more importantly, it is the change in volume that plays a big role, because it adds a compressive pressure in front of the crack tip, and that reduces the stresses in terms of their tensile magnitude in that area. So what you see in those cases, you see microstructures that they look like this, where the white background is the cubic phase, the gray is the tetragonal untransformed zirconia, and the black is the monoclinic transformed zirconia. And you will see that the transformation is happening around a process zone, if you wish, of around the crack that propagates. And essentially, this kind of increased toughness has actually made the use of this material to be quite widespread, especially in dental applications. So we'll stop here we'll stop here with a discussion on fracture and fracture toughness, and we will move forward in the next lecture when I come back to Drexel with fatigue. Okay, thank you.